What specific problem does the Agent Lightning Framework aim to solve in the context of training AI agents with large language models?
The Agent Lightning Framework addresses the significant challenges of training AI agents that utilize large language models, LLMs, in complex multi-turn scenarios. It specifically aims to decouple agent execution from reinforcement learning, RL training, allowing for seamless integration with any AI agent without requiring extensive code modifications. This decoupling is crucial because existing RL methods are primarily designed for static tasks and struggle with the dynamic and diverse nature of agent interactions, which often involve multiple LLM calls and external tool interactions. By formulating agent execution as a Markov decision process, MDP, and introducing a unified data interface, Agent Lightning enables efficient data collection and optimization of agent behaviors based on real-world interactions. Ultimately, this framework enhances the adaptability and performance of AI agents in real-world applications, overcoming the limitations of traditional RL training approaches.
How does the proposed Agent Lightning Framework work? Please illustrate step by step, focusing on the decoupling of agent execution and reinforcement learning, RL training.
The Agent Lightning Framework operates by achieving a complete decoupling between agent execution and reinforcement learning, RL training, which is fundamental to its design. First, it formulates agent execution as a Markov decision process, MDP, where the current state represents a snapshot of the agent's execution, and actions correspond to outputs generated by the policy LLM. This allows for a unified data interface that structures agent trajectories as sequences of transitions, each containing the current state, action, and reward, abstracting away the complexities of agent orchestration. The framework consists of two main components: the Lightning Server, which manages the RL training process and exposes an API for model updates, and the Lightning Client, which runs the agent and collects data without requiring code modifications. This architecture enables developers to optimize agents with minimal changes, facilitating the integration of RL training into diverse agent frameworks while maintaining flexibility and scalability.
Can you provide a detailed example of how the unified data interface operates within the Agent Lightning Framework during an agent's execution? Walk through the main steps involved and how data is collected.
The unified data interface in the Agent Lightning Framework operates by capturing relevant data during an agent's execution, which is structured as a sequence of transitions. Each transition consists of the current state, the agent snapshot, the action taken, the output generated by the policy LLM, and the associated reward. For instance, in a typical retrieve-augmented generation RAG agent, the execution begins when the user inputs a query, prompting the agent to invoke the LLM to generate a search query. This action updates the state, which is then recorded as a transition containing the input, output, and reward. As the agent continues to execute, it retrieves relevant documents and generates a final answer, with each step similarly recorded as transitions, allowing for a comprehensive collection of data that reflects the agent's decision-making process and performance. This structured approach enables effective reinforcement learning by providing clear trajectories for optimizing the LLM based on the collected data.
What are the theoretical or practical benefits of using the Agent Lightning Framework compared to traditional reinforcement learning methods for optimizing large language models in agent scenarios?
The Agent Lightning Framework offers several theoretical and practical benefits over traditional reinforcement learning RL methods for optimizing large language models, LLMs, in agent scenarios. Firstly, it achieves complete decoupling between agent execution and RL training, allowing for seamless application to any AI agent with minimal code modifications, which contrasts with traditional methods that often require significant adaptation of agent logic. Secondly, Agent Lightning introduces a unified data interface that organizes agent-generated data into structured transitions, simplifying the data modeling process and alleviating issues related to accumulative context length, which is a common challenge in traditional RL approaches. Additionally, The framework employs a hierarchical RL algorithm, Lightning RL, which enhances credit assignment and allows for flexible context construction, enabling more effective learning from diverse agent interactions. Furthermore, the training agent disaggregation architecture enhances scalability and flexibility by separating the RL training process from agent execution, thus optimizing resource utilization and improving training efficiency. Overall, these innovations position Agent Lightning as a more adaptable and efficient solution for real-world agent optimization compared to conventional RL frameworks.
How was the effectiveness of Agent Lightning validated through the experiments presented in the paper? What metrics or benchmarks were used to evaluate performance?
The effectiveness of Agent Lightning was validated through experiments on 3 distinct tasks: a text-to-SQL agent, a retrieval-augmented generation RAG agent, and a math-focused question-answering agent. Each task was implemented using different agent frameworks, demonstrating the framework's versatility. Performance was evaluated using specific metrics such as answer accuracy for the text-to-SQL task, which involved generating executable SQL queries and assessing the correctness of the final answers. For the RAG task, a weighted combination of format and correctness scores was used, with the correctness score calculated as the word-level F1 score between the predicted and gold answers. The Math QA task's performance was similarly assessed based on whether the agent correctly answered the questions, showcasing continuous and stable performance improvement across diverse scenarios.
What limitations did the authors acknowledge regarding the Agent Lightning framework, and how could these affect its applicability in real-world scenarios?
The authors acknowledged several limitations regarding the Agent Lightning framework, particularly in the context of extending reinforcement learning (RL) paradigms to agents. One significant challenge is that existing RL methods are primarily designed for static, single-call tasks, which may not adequately address the complexity and diversity of agent interactions that involve multiple LLM invocations and external tool interactions. Additionally, while the framework allows for flexible training and optimization, it may still struggle with the intricacies of dynamic agent behaviors and the need for tailored reward structures in real-world applications. Furthermore, the reliance on a unified data interface, while beneficial for abstraction, may not capture all nuances of agent execution, potentially limiting the effectiveness of the training process. These limitations could hinder the framework's ability to generalize across various real-world tasks, especially those requiring intricate decision-making and adaptability.